Hello. I'm going to be, as I say, talking about some iPod stuff. This is kind of about 9 months of research crammed into about 50-odd slides. We're going to talk a bit about some history of research into iPods very briefly, and then we're going to talk into basically how I hacked some iPods that no one had hacked yet. Follow me and Freddy. So we're going to be talking about iPod Nanos specifically. This is the iPod Nano 5, and at the point of me starting this, we had some boot ROM bug that a guy called Q3K, who does a few other talks, had found, which meant we had full kind of control over this device and could use it as a research, a starting point for our research. But we didn't have anything for any of the later devices. These were basically how the bug was patched. We didn't know how it was patched or why it was patched, but it didn't work anymore. So I set out, after reading the blog post talking about the boot bug, I set out to basically solve that problem and see if we could figure out how these devices work. What OS do they run? Are these iOS? They might be. They're not. Do they have any secret features? They do. And did Apple do anything weird? Yes. So we'll start by talking about some firmware. Basically, they work very similar to OG iPhones. So image 1 containers, everything is signed. Basically, everything is encrypted, except the actual resources. So things like images, databases, stuff like that. But because it's signed, we can't modify anything. So these are inaccessible entirely. We can't put any data on them except music, pretty much, in theory. The actual files start with header that looks like this. Which the only field that matters here is that they have names. And there's multiple partitions for multiple different boot modes. There's a recovery mode and a regular mode, which are kind of the two important modes for this. And weirdly, the signature doesn't include that name for some reason. I mean, you can technically change it. Of course, there's only a few preset options that you could use, but that's weird. And when I saw that, I started looking into this a bit further to see what you could do with that, essentially. Well, if we look at how the boot process works, when you press the power button, it checks, are you holding the two volume buttons? And if you are, it goes into a recovery mode, like that. But it doesn't check the signature on the resources. This is funny because you should never be able to access any of those resources from that recovery mode. That recovery mode has its own because it's designed to assume that the rest of the firmware is corrupted and gone completely. Except, what if we could change that? As I mentioned, we can change the name of partitions. So what if we just swap the recovery mode and the normal mode around? If we do that, you end up with this thing we call disk swapping, which is one of the first bugs that I found. This is a boot ROM bug, they can't patch it. And essentially, if you swap those partitions around and pull out the volume buttons, it will load with completely unsigned resources. So you have a massive attack surface at this point. This was the first big breakthrough. And when you look at what's in there, there's images, there's databases, there's audio. We had some of this already, so it wasn't really new, but it also has fonts. And fonts are really hard to do correctly. So they probably took somebody else's code. Font formats are infamous for the history of lots of exploitable bugs. So let's look at what the older devices used to get an idea for what they might have done. Well, the Nano 3 kind of first one that I had access to, had a look at what they used, and they use a version 3 type from 2006, which makes sense because that was probably about when they started working on it. And then on the Nano 4, they didn't bother changing it. Yeah, they've never changed it. Ever. 2006 is really old for this, and there are a lot of really good bugs, but there is one in particular that's quite interesting, because I've got the size of the wrong order. Yes, there is this bug is present in that version 3 type at CD 2017-97, which basically is a really trivial bug where they don't check when you are they don't check when you are doing any operation other than push if you have overflowed the stack. So essentially, any operation that pushes but isn't push will cause corruption. And OTF fonts, like one OTF font specifically, there's newer versions of this, but this is the original version, has essentially every single character, every string that you render on the screen is a program that gets executed, and it uses that program to compute lots of properties about the font, how tall the character is, how much space between the letters, etc. And it can do normal VM things, like control formats, but it can also do kind of graphics-focused things as well. These aren't really used anymore. I don't know how modern ones work exactly, but they've kind of got away with a lot of this because this is really hard to do correctly, as I mentioned earlier. And hence we get bugs like this. There are a load of operations that do operations on the stack that aren't the push instruction, and these are kind of the 3 important ones that we care about. We can push random values, we can swap the current value with the previous value, and we can move down, essentially just pop. And that is all you need to turn this bug into code execution on these devices. So to give a walkthrough of kind of what these do, this is kind of what the stack looks like, very, very simplified. And if we do a push, we get a value, and we move the stack pointer up. If we push a random value, if we push another value, it goes on top. If we push a random value, then it ends up out of bounds. We, at this point onwards, can't use any push instructions, so if we want to move values around, we have to find ways to do it without using push, hence why we push this random value. But then we have this exchange operation. This exchange operation is really useful because it means we can move that control value into the out of bounds slot. And if we keep exchanging things, we can actually move things further up. If we actually look at what kind of the structure that defines this stack, it looks like that. I've removed a bunch of stuff here. This stuff is huge. But you've got your stack with a fixed size, and then you've got these zones, and zones are used for defining subroutine calls, because apparently you can do a function call in a font. The interesting one here is zone, and zone, every single time you run an instruction, gets set to the first element in the zones list, the current element, but we never do a function call, so it'll always be the first one. And the position is quite important, but build chart, learn, it'll be relevant later. That's good. Got a bit messed up, didn't I? So essentially, if you've written out of bounds up until you get to zone, your stack will kind of look a bit like this. We'll use the kind of messed up slides here. If we, at this point, do an exchange operation, that zones field will get moved down and overwrite the previous random value we pushed, and then our controlled value will go into the zones field. But because it does this overwriting thing every time we perform an operation, it will actually get set to zones again, which means we have two copies of this controlled, of this known pointer. This is really useful because kind of a completely blind scenario. We don't know what anything looks like on this kind of device. We don't have any debugging, so we need to make our exploit for this work completely blindly and reliably. If we keep kind of pushing, keep swapping, we will just move that value anywhere in that structure. And as we mentioned, there was that build chart at the end. If we move our zones 0, into there, then we get an interesting primitive, because build chart is technically supposed to be used for kind of reading and writing temporary storage, because fonts apparently need RAM, their own memory. But what we can do is turn this into an arbitrary rate, because if we overwrite build chart and we change the length to something random, then we essentially have the ability to poke and peek any memory relative to that zones. So we can move, we can edit anything after that first element of the zones field, which includes that build chart field. Which means we can set length to anything we want, set pointer to anything we want, and then we can write our own code anywhere we want. So we can now execute code on these devices. Sort of. The problem is, the code is still encrypted, so we don't know what any of it looks like. Maybe we can dump it, but we don't know how. How do you get anything out of it when you don't know how to access any of the I/O? We don't know how any of the devices work, because Apple famously does everything themselves and documents none of it. And yeah, how does any of this work? We could try playing it as audio, and listen to our firmware, but that is, I'm scared of analog, and I don't know how audio works. So that is not what I do. We could do it via just dump a file. That would seem to be the trivial option, just write it to a file, plug it in and pull the file off. We don't have a clue how files work. The storage on these is bizarre. For some reason, when Apple designed the iPod Nano at least, they put a chip specifically with the ability to have an audio coprocessor to optimize audio and make it sound good, and then didn't use it, and then realized they had this kind of wasted block on their device and were not using it for anything. So came up with a really smart idea of putting the file system driver in the audio chip. So you play sound to write files, and the audio chip was a random Samsung chip that has no documentation ever and never was used in anything else. So we are still trying to figure out how the Flash works. Maybe we'll eventually figure it out. It'll be useful if we want to put any other OS on it. So if anybody wants to help, there'll be links to John or Discord there. The other option is we could do USB. USB is hard to do generally, but we might be able to abuse some of the parts of USB. Specifically, when you plug a new USB device in, it basically sends some identifying strings, manufacturer, product name, etc. And those strings probably appear somewhere in our firmware, so we can try and find them. If we can, then we can copy bits of our firmware to it and try and print them out very slowly. The problem is we have to find those strings first, and we still don't have a way to get any info out of these devices. So what we try to do is crash the device a lot. I'm really good at doing this after a lot of trial and error. So it turns out if you jump to some invalid memory, it will reboot. Or if you put it in a while loop, it will hang forever. So we can actually use that to leak one bit of data of whether or not our device is essentially has a value within a certain range, for example. So we can use binary search to search through the entire RAM of the device looking for the string apple and hope that that's the one that it prints when you plug it in over USB. Turns out it is. So if we find it, we crash. If we don't find it, we hang. And that is essentially how we can make single bits. We can slowly narrow our range down until we eventually know where our magic string is. This takes a long time, and it has a really slow data rate. For what it's worth, that would take, I think it's 300 years to make the whole firmware. I'm not likely to be alive in 300 years, so that's not really going to work. But now that we've got the string, we can just print out our data. So we essentially just write some code, essentially just find somewhere where it will run, and keep unplugging and replugging the device in, and have it very slowly move the data that it's copying, so we can very slowly get bits of firmware out. And I left this running for about 8 hours. Turns out, for some reason, it reboots after about 8 hours, so you have to just restart it. I think that's a bug in the USB stack, but I actually have no clue. And if you leave that for long enough, you eventually get your firmware. That is an example of what it looked like when I was doing my testing. So just overwriting that string with A is to print what is next to it, hoping that what was next to it is the code for actually copying that over USB. So now we just find some USB code. We've got our own backdoor, essentially, so we can go read this log of memory. And skipping over a couple of steps, we can actually get the boot ROM. So this was the first public dump of the iPod Nano 6 boot ROM, the first dump of a S5L, or whatever that number is. And we could also see how they patched the boot ROM bug, which seems to be somebody just came into the USB code one day and randomly added an if that wasn't there before. The iPod Nano 7 is almost the same, but the problem is they changed the USB port, and they changed it from the fat 30-pin connector that some of you might recall to Lightning, and Lightning requires a lot more setup to actually get it to work, and it really did not like being unplugged and replugged. So I had to find another way to get data out again. So we could go back to the drawing board, we could try looking at files, we could try looking at sound. Technically these have Bluetooth, we could look for Bluetooth. Well, the way they did Bluetooth is bizarre. They essentially brought a user space sort of emulator for iOS and then copied the iOS Bluetooth stack, pretending that it was an iPhone. But we also have a screen. The nice thing about a screen is if you know where the place it reads the pixels from, which I just assumed they hadn't changed, thankfully they hadn't, you can write whatever you want. So if I want to get data out, all I need to do is write my own GPU driver and assembly. Step one. Thankfully, there's actually an example of how to initialize some of this that was figured out when people put Linux on the earlier iPods. So I had a bit to go off, but yeah, trying to this took a lot of trial and error. And then if we take 2 bits of data, you can map them into 4 characters by just making a lookup table. So I actually used that lookup table because you can type it with one hand, which is really useful because you slowly can print the data onto the screen and then retype it by hand. Which looks like that. Repeat indefinitely. And essentially this is sort of start from a known string. I basically went through every instance of Apple Inc. in this firmware and typed out what was after it, looked if it looked like the right code, manually calculated every branch to follow it through, slowly dumping out bits, functions. So eventually I found the same USB code that I found in Analog 6. And with that, I could basically repeat the steps and get the first boot ROM for the 8740 as well. So these were at the time the first and only way to jailbreak iPod Nano 6 and 7. But things have actually came on since then. That was the state at the end. So that is kind of where I essentially took a break. But there were actually some kind of things that happened after. So Super Diags is essentially none of this was necessary if I had have spent some time and actually looked at all of the possible vectors before going to the first one that I found. So that's a good kind of thing to take from this talk, is survey everything before just diving into the first kind of bug you find or technique that you find. Essentially, the debug menu exists buried by some key combination on every iPod, but to get to it, you need to access it via serial. There is no driver for serial, but they left the console in, which has the ability to read and write all of the memory of the device, set breakpoints, etc. You essentially have full GDB almost. But, as I say, there's no driver, except the actual way these images are packed means you can take modules from other take modules from other firmware partitions and put them into the Diags partition. And they actually shipped all of the required ones in the main firmware and in the tool that flashes the firmware, which is called WTF. Where's the firmware? So if you pack that all together, you essentially can make a fully debuggable iPod without having to do any exploitation at all. So someone figured this out and had this popped up in about 2 hours and replaced 9 months of work, and it's more reliable. Don't have to hold buttons. Also, actually going over surface that other people have said they've already looked at. So the boot ROM, after having the original bug was patched, I decided it wasn't worth spending any time looking at in detail. It had been researched to death. It mustn't have anything in it. I was wrong. So S508 is a bug found by someone called Gish. That's probably a butchered pronunciation. Which essentially is when you upload firmware, you send it over USB a blob of data, and it copies that to a global variable. There's no size limit on the firmware you can send because they didn't want to put any restrictions on it. They also don't prevent you from going off the end of RAM, which loops back around again. So if you just send it a 100 meg file, it allows you to overwrite all of the code from the boot ROM as well. If I had have looked at the boot ROM, then I might have found that. And that's really nice because you can get code execution essentially from the earliest possible point, which is really nice if you want to do things that put Linux on it. This is pretty recent. So this is again, Gish is working on a port of Linux. So eventually there might be a full Linux distro that you can run on an iPod, which I think is quite fun. That is pretty much everything. I'm going to do that quite quickly. But join our Discord, QR code, and then the other QR code linked to the GitHub, so you can get all of the code. Thanks to B-Sides for actually letting me give a talk. Thanks to QCK for finding the original bug. Thanks to MJ Walsh, who worked at Apple in about 2006 and didn't ever update FreeType. Essentially, I would have never been able to do any of this without this. Thanks for listening.
When you got it to print out the firmware bytes on the screen, were you thinking of using any image recognition to just automate it, or were you doing it by hand?
So I did end up doing it by hand, but I did speak to somebody, and they said it would have been really funny if I had have printed the whole thing and did some OpenCV magic with a webcam to actually read it out. It would definitely be doable, and if I had to do any more than the small amount that I did, then I would probably look at ways to do that. So even if I hadn't been able to kind of get the other techniques working, then that's how I could have done it. And I went through that really quickly, so if anybody has any other questions. Yeah.
So firstly, I've linked out firmware over an ND before, so I feel your pain. So, well, I was interested in, you mentioned you got a new function of the USB set. You explained how you did that. That's really how did you go about putting something in the USB set without just doing press?
So essentially, the USB stack has a bunch of vendor commands. So you can send these kind of there's a command line tool called like _something, which allows you to essentially send raw bytes as a vendor command, and you can use that to implement extra functionality. Apple uses this internally a lot for iTunes. So things like syncing, send special vendor commands to put the device into certain modes. And there's ones to reboot the device. There's one to wipe the device, as I found. And I took one of those kind of branches in that code and replaced it with a just tiny shellcode stub that would take an address, read that address, and give me that value back. And I kind of just guessed what most of the functions did around that. So yeah. Oh, I've lost my slides. Oh, no, there they are. Anybody else? Well, if that's everything, then thank you.